recommend that you all take a minute to go over to your grade book, look, make sure you don't have anything missing, okay? Because this is the last chance to turn it in before you get a semester grade.
I did it a couple days ago.
You what? Did it a couple days ago?
Yeah.
Okay.
I didn't see you.
So
You said something, but I looked, I didn't see it.
I've got, well, pay attention. All right, so Sydney, your 16 lab, I think is all I had. So that's not due till today. Michael, you're good. Who else? Ivy has some stuff, but she's not here. Kai has some stuff, but she's not here. Shannon, you had something. I know you did. Shannon, you had last week's questions.
Yes, I just handed to you.
Perfect. Dylan. I don't think you're missing.
To the front of the camera.
Oh, you had the one thing, but you did end up handing that in. And that's all I got for you. Yes, Ethan. No, it's looking at me. It's on, but it's looking at me. You got nothing. Start. You owe me lab 14. Don't have it.
Oh, you literally live in the same house as her. How do you not
And
have
16, which should have been the one turned in today. Aaron, you're good. And Lily, you had what? Lab 13?
Yeah, I turned that in.
And then questions, which were due today. So you're good. All right. So no biggie. Not a lot of stuff. And there's no lab to take home and work on this week, right? Because that's kind of the idea, is let's not take it at home and I'm only working on stuff.
No homework this week, so I can prepare for the midterms.
And the test.
Oh, yeah.
Oh, thank you. Excellent. Where am I gonna put that?
Please
Right
don't
here.
make noise.
All right, let's see.
What?
Lily, back at ya. Oh, that's Jackson's and Jackson's. I should have given those back to him. Sydney.
Oh, Aaron, this is your
Michael.
lab from today.
Aaron.
It's
Shannon.
Yes, it's your lab.
Sydney
I didn't even
again.
turn on my light.
Michael
Wait, no,
again.
turn it mine too.
Ivy, Kai.
Yeah, you don't even have to get up.
Kai, Dylan. E. You even put E on it.
You're in the labs, aren't you?
Aaron. Very good. Okay.
Aaron's
Yeah.
in his lab.
All right. So that should be.
Aaron's the most active. Physically active lab.
Shrev isn't here. All right. That should be good. Nobody ever claimed that one. So, yep.
The orange or the compliment.
All right. So let me go to share screen. All right. So let's go over today's notes and then let's spend some time reviewing. Okay. Sound like a good idea?
I love that idea.
Yeah. So this midterm is not the end of the world, right? Because it's not weighted more than anything else you're already doing. It's more a gauge to see what you've hung on to cumulatively, right? What have you hung on to from the beginning? That's a fun one. What you've hung on to since the beginning when we started, as opposed to cramming week by week, right? All right. So you're gonna have, let's see. Oh, and also real quick, where is it? Real quick, okay, so you have the special assignment, right? And that is the food. Remember what you're bringing? Katie's bringing yours. Katie's gonna help me proctor exams. I'll have an extra set of eyes. She'll help me do that, which will be great. All right, so if you're January to March, where are you? Just me. Okay.
No, I'm
So
January.
that's you. All right. So remember, it's bring a food item theme to represent any concept, topic, scientist, or lesson from this semester. So I've got January to March. That's something sweet. That's you too. All right. April to June. Who's that? Bring something salty. Okay. July to September. That's a lot of you. That's something savory. Okay. And October to December, something healthy, okay? And
Aaron
you
got the
may
easiest job.
want
He can just bring us
to,
carrots.
you guys may want to get on the lab, on the forum and just communicate, because you guys don't necessarily know which other kids share your birth month in the other group, and their assignments are the same. So we could end up with like 4 veggie trays or.
Well, since there's so many people in Savory, do you think like some of us could like disperse out in the other group, so it isn't just like one.
You find that something sugary.
Yeah, I make.
We have plenty of sugary. So for savory, it can be real easy. It can be like, oh shoot, it can be like a cheese tray and cheese and meat. I mean that's savory, right?
Or waffles.
Or
Or
let me
waffles.
get a take towel, It's-
Just drifting, bro.
Everybody in this room.
Whole grain gold.
Oh, it's so nasty.
It can be warm, it can be cold. So it just has to cover a topic that we've had this year or a concept. So that we did cover a little earth science already. So there's some things there that you could harken back to. Maybe it's just a fun name, whatever. Be creative, check Pinterest. Pinterest is where you find these things, right?
Dude, I love Pinterest. I love you.
I love Pinterest.
She has cool wallpapers, but other than that,
I've literally never.
Yeah.
That's like the. That's like the
So it does say, remember no peanuts, all right? And your item should serve 20 to 30 because there's a bunch of us.
Yeah, just give me
If
a
you go
few
less than
more
that,
colors.
don't worry about it. I imagine
Then
some
we can
parents are
still
gonna
use
hang,
it
that's
as
why I
a-
suggest to be a little on the hefty side. All right, so heading into today's lesson.
Now, when is this?
Next week,
wait, real quick question.
yeah.
Can
Tuesday?
you define the difference
17.
between sweet and savory?
Yes, please.
So really?
Just
So-
double check.
So sweet is
Is
sweet,
a nickel a coin?
like involves a lot of sugar.
Yeah.
Hang on, guys. Savory is basically it's something that's not sweet or salty. So it can like sandwiches, chicken. These are all things that
I
are
would disagree, because I would
savory.
say savory.
I would disagree. I don't
Savor.
care. I
You're
don't
just
care.
savor.
Yeah,
I don't care.
You
We
do
can
say
say
there.
You're not a part of
I
this.
don't
You're
care. I am
savor.
not. I am
Yeah.
not. I am not.
Oh,
I am
the
not.
fact that you just screamed, "You're not a part of this," is kind of funny to me. You're not a part of this.
But, like,
They had an interesting
I
weekend.
savor
We split this way.
Y'all have
Yeah.
like some
Savor.
unheard of like conflict between you two now. Or
Well,
you two, like,
the question is a nickel a coin? That's the big one.
Is it the nickel a coin?
Yes.
Yes.
What else would it be?
Does anybody here believe that a nickel is not a coin?
I know.
No.
Of course, Henry.
He,
I
he-
know.
he
Wait,
did
wait,
agree.
what did he say?
He did agree. It just
Yes.
took him like 30 seconds.
He was
And he
just
had to-
wasting time.
And you had to explain what a bank note was.
Yeah, no.
Yeah.
because I said-
You should just
I
said
said
it's a yes, it's a yes or no question.
I
It's a yes
think
or no
better than
question.
because I go,
All right, everybody have their notes out.
I think that a nickel is a coin.
Good.
Good.
I did my notes. I just left
Smart.
it.
Yes.
I
Notes
don't
out,
think
notes out. Hey,
Yes.
notes out.
What?
All right, what's your first blank?
Induction.
Yeah, notes out. That helps. There we go.
Induction.
Wait. Like trying to ask me a question, I think you go through it. Like, oh,
Induction.
Okay.
Not technically. It's broader than that.
Heat.
alright.
Mhm.
Okay, Jimmy.
I still don't see everybody's notes, so I'm waiting. Like, where are your notes? Mm-hmm.
Well, it's not.
Do you not have yours? You have yours?
Cool.
Yes, that is. Ethan's getting his. All right.
I'm using the book.
So, heat is the transfer of thermal energy from one object to another, right?
You're out of it.
Which way does heat flow?
Up.
Well, yes, it does go up, but
To a fluid object.
Heat flows spontaneously from hot objects to cold objects.
yes, from hot objects to cool objects. So when you put the ice cube in your hot chocolate, you are not putting the cold into the hot so much as you're putting the hot on the cold, right?
Danny,
Yes.
what's rancid and what's more?
I'm sorry, what?
What'd you break?
I didn't break anything. It just made magnet.
Oh, we'll get there in a minute. We're not there yet. I'm like, what are you talking about? All right, so temperature. All right. So this goes back to the lab. All right. Temperature was the measure of how hot or cold an object is compared to a reference point. So
Like I am cold.
this has to do with how fast the particles of the material are moving. So your reference point is going to be a scale, and you have absolute zero on the list here for number 2. Absolute zero is the lowest temperature theoretically possible. And at absolute zero, the motion of all particles that constitute heat would be minimal. And that's 0 Kelvin, and 0 Kelvin is measured as negative 273.15 Celsius or negative 495.67 Fahrenheit. Can we get to 0K?
No.
No, we cannot. It is what? Theoretical. So the idea is that if you could cool something to the point where all of its, molecular, atomic, subatomic particles cease to move, yeah,
Suspended
you need
animation.
more than ice, huh?
Suspended animation.
There you go. Yeah, essentially you would get 0 Kelvin, where everything stops moving, and there you would get the lowest possible energy from that object. So if you look at the scales, this is what you were asking, Henry.
If everything stopped moving, would it stay at absolute zero forever?
Well, we don't really know because we can't get anything to absolute zero, but I imagine it would be hard to maintain it. I mean, it's hard. You can't get to it, so I think maintaining it would be even harder than getting to it. So if you look over here at the little temperature chart with all the thermometers, all right?
Well,
We have Celsius. You can see it's on your page, right? So you've got Celsius, Fahrenheit, Kelvin, Rankine, and Rammore, which is what Henry was asking about. We don't use Rankine and Rammore typically. I think maybe some fancy physics folks do, but we're not going to be using them. So basically, the similarity between Kelvin and Celsius is that the scale is the same, meaning that the delineations between one measurement and the next measurement are exactly the same. Does that make sense what I'm saying?
No.
Okay, so if you have a Kelvin scale and this is, 1 degree to 2 degree Kelvin, the same size on the Celsius scale, okay? But the Kelvin scale, as you can tell in this picture, goes way down. So if you look at the boiling point of Kelvin, it says it's 373.15.
I know, but Kelvin is just shifted Celsius.
Right.
I'm smart.
And so there you got your Fahrenheit. And Fahrenheit's what we use. And that's what makes sense to us. But boy, is it complicated to remember
it's just dumb.
all these strange numbers, 212, whatever. So your body temperature at Celsius is about 37, okay? And we're used to saying 98.6, right? So if you are in Europe somewhere and you're vacationing and they say it's 19 degrees outside, it's probably, please stop. It's probably really nice weather. But if you're here and they say it's 19 degrees outside,
Still awesome weather.
no.
Yeah. Yeah.
Horrid weather, way too cold.
No,
That's not too cold.
no.
Not
Not at all.
I mean, if it
That's
would be
perfect.
awesome if it was snowing and it was like 90
Yeah, that
degrees.
may be, but man.
Snow here every 2
Yeah, every
It
couple
does
years.
snow.
We had a good snow 3 years ago, so I'm hoping we're due.
I want to snow.
So basically what you need, I know, I do too. I do too.
You can't.
So basically what you need to remember is that Fahrenheit's used predominantly in the States, Celsius is used in science and everywhere else, and Kelvin is used for absolute zero, or basically if you're working with something really, really cold and you're trying to, be more representative of how close it actually is to your theoretical point of all motion stopping, all
What about
energy.
raw and gray?
Yeah, those, like I said, those are just very uncommonly used. I'm truly not even sure what fields use them. I want to think it's like certain physics fields, but I've never used them. It's interesting that they're there though. So your book only mentions the 3, which is why I gave you this graphic, because it shows you that there are more than 3, right?
Well, it's tell me what they were.
Exactly. So temperature is related to the average kinetic energy of the particles in an object, and there was a spell right there, due to their random motions through space.
I
So,
found that out.
Here's your question. Why then why does the random motion of particles, if that motion energy is put into the system and the motion of the particles increases, why does that make the temperature increase? What occurs with the particles? Can you think about it?
Was there more friction?
There you go. It's friction. Absolutely. So they're bouncing into each other. The more they bounce into each other, the more friction, and then the hotter it
Friction
gets,
creates-
right?
Something about your eye.
All right. So also, what is Henry? Henry, stop. All right.
What?
So I don't know, but
Welcome to the gift of love.
Henry, everybody has an exam next week. We need to get through it so we can go over. Yeah? All right, so we talked about this last week. So if you were to put your hand on this table, does it feel warm or cold? Okay, if I told you that the temperature of the room, the ambient temperature of the room is probably about 69 or 70. What is your guess? Okay, Henry, thank you. Henry, sit. What is your guess as to the temperature of the table?
Yeah.
Yep, it's probably really close. Why is that?
Just conduct. It's just.
I
don't know.
So it's been sitting in this room for like a long time. This table hasn't left the room in years. So it's been sitting here for quite some time, and it should be at an equilibrium with the room. It's not like we just took it out of the oven or the freezer. I mean, if I took a pan out of the oven, it's gonna be hot. It's gonna be warmer than the counter I put it on, right? So here sits the table. I don't have an oven big enough for it, and it feels cold. Why does it feel colder than 70? Why, Ethan?
Because it has it's colder than everything else.
Well, if it's about, technically, it's about the same temperature as the room and everything in the room. So why does it feel colder? Cold?
It has to do with you touching it. If anything else touched it, it would feel. It would be. No. It's because the way it conducts.
Yes. Yes. What's it doing? It's conducting heat
It's
from where?
taking the heat from your body.
Yes.
And trying to suck it in.
Exactly.
And you.
Because heat moves
That's why if
from.
you touch it with something else that wasn't your
The
body.
hottest to the coldest.
So Ethan, if you put your hand on the table for a minute and leave it there for a good minute. So when Ethan takes his hand off the table, I'm going to ask him to do two things. I'm going to ask him to touch his other hand to the spot on the table that his hand that's currently there was touching. And then I'll ask him to touch the hand on the table to his face. So touch the hand on the table to your face, and how does it feel?
Cold.
Now touch your other hand to the spot, and how does it feel?
Warmer?
A little bit, yeah,
Because it's
Wow.
right. So the heat went from
Shut up.
hot to cold. All right. So temperature is related to the average kinetic energy of the particles in an object due to the random motions through space because they're bumping into each other and there is friction, right? Thermal energy depends on the mass, temperature, and phase. There should be a comma in there. Mass, temperature, and phase of an object. So let's see here. This is like the difference between trying to take the temperature of a hailstone versus an ice sculpture.
Wow.
Right? The hailstone's going, it has less mass. It's going to start melting. It'll warm up more quickly than the ice sculpture, which has more mass, right? And it's phase. So by phase, we mean solid, liquid, gas, right? All right, who remembers what I told you last year about idiots on the internet and snow? Who remembers that? Do you remember, Lily? Wait a minute, Lily, go ahead.
Everyone thinks that, oh, the snow's made out of plastic. It's a government sham because they held up a lighter to a snowball and I forget exactly
It
why.
just disappears.
What happened?
Yeah, because the moisture moves to the other part of the snow, right?
No,
No?
It turned black because the water evaporated so quickly it sublimated. So it
The
goes
black's
straight
from the butane, but yeah, it's sublimated.
yeah, it's
So
sublimated,
every year,
exactly. So the black is what's left.
People are
from
like,
so the
it's
dirt,
just polluted.
the dirt and butane. And
Yeah. so for those of you who weren't here last year, you say you want to snow,
the-
right? As soon as it snows somewhere, some nitwit on the internet, okay, wherever it's snowing, is going to make a snowball and hold a lighter to it and then claim it's not real because, oh, the government conspiracy for fake snow. I don't know why the government would want fake snow, but they'll light it on fire and the snow will not melt. You will not see it turn to liquid. It will just disappear because it is skipping that phase. It's sublimating. It's going straight from a solid to a gas, it's skipping liquid entirely. And it'll get black because the butane has waste when it burns off. There's soot. Every year, I swear.
I want to try that now.
It's my favorite when these people come on. I'm like, oh, it's them again.
Like,
So,
what's these idiots?
so then we have this idea of thermal expansion, which is also what your lab just entailed, right? Oh. So thermal expansion is an increase in the volume of a material due to a temperature increase. All right, so when you're riding down the interstate and there's no radio on and you're listening, what does the car sound like? You ever heard the sound that goes, what is that?
Things on the road you're bumping over.
Yeah, what are those things?
They have ruts in the road too.
They're not ruts.
Well, also, when you go over bridges and stuff, they have big connections.
Bridges have teeth. Yeah. So when you drive down the interstate next time, pay attention to this click, 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 click. Those are expansion joints. If they made it one solid piece of pavement,
It would
then
be
when the
epic.
material expanded, it would crack. So they make it in segments. And then they put this rubbery material in between. So when it gets hot and the concrete or asphalt, whatever they're using, expands, it mushes into that little cushion and doesn't crack. So there are expansion joints in highways. There are bridges tend to have, you ever seen them look like teeth, like big metal teeth like this? And they do this sort of thing as it gets hot. So that's really necessary to understand something like thermal expansion when you're dealing with engineering. Now, here's the question. For those of you that did earth science and we talked about weathering of rocks and we talked about how ice can split a rock. So if things expand when they get hotter, how does water fill into the crack of a rock, freeze, and then break the rock?
Because
Some
it
air in the
continues
ice.
to expand because ice is when it freezes or water freezes, it turns into ice.
Hello?
Ice.
Yeah, when
But
water
you're asking
freezes, it
why
turns into ice.
if when things heat expand, why is it when it gets cold it expands?
Mm-hmm.
I don't know.
Because it's not as packed, or it can't be as
Getting
packed.
there.
It can't be as close packed as a thing because there's
So you
strong
ever,
bonds, so the bonds can't.
Anybody wear a ring regularly?
No.
No.
Oh, okay. When you do, and you go outside in the cold, your rings will slide all around because your hands will contract. When things get cold, they contract,
Yes.
right? So when you get cold, or when anything gets cold, the matter contracts because there's less energy in the material. There's less bouncing and moving around of the molecules. They're tighter together. So what happens when you freeze water?
The molecules slow down.
And then what happens to it?
And they expand.
They
because
expand.
have to have perfect.
There you go. So
ridges and
water, for
connections.
example, you have your particles bouncing around, right? Bouncing, 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 bouncing. They get really close together and they get
And you
as
bounce.
close as they can get at 4 degrees Celsius. That is the most dense water can be. Because after 4 degrees Celsius, it starts to freeze. And
Wow.
when it freezes, they go from bouncing around and being like right here to locking into place in a crystalline structure. And that causes it to expand. That's why you can't take a can of Coke and put it in the freezer and come back for it, 6 hours later. You could probably come back for it 20 minutes later, but once it's frozen, anybody ever put a soda can in the freezer and forgotten about it? Yeah, I've done it. It's fascinating, isn't it? It's like an epic explosion.
It
Yeah.
happens to my aunt in the hotel room.
Because it breaks the can open, right? It expands to the point where it just goes bang.
Well, do you
We
think?
heard it.
Oh yeah.
We were like, what the heck is
Yeah.
that?
Yeah.
Well,
That's
could
cool.
you just like maybe pop the cap open just slightly?
Yeah.
And then
Yeah.
that would make it
It would still come out, but it wouldn't explode.
better.
hmm
Coke
That
stuff.
sounds cool.
Anybody ever filled an ice tray right to the tippy top? It rises up, right?
I've seen that.
Yep. Or a bucket. If you fill a bucket to the tippy top and leave it outside, you come out in the morning, it's like this much taller. The water is frozen, it's coming out the top because the ice will expand. So typically things are going to contract when they get colder,
Okay.
right? Well, I've done it because like we used to have our Christmas tree outside when I was a kid. We'd leave it out for like a week before we bring it in. And the bucket would be full of water and we'd get a freeze inevitably and the whole thing would be raised up. The tree would be frozen in there and you couldn't get it out. So everything is going to expand when it gets warm, contract when it gets cold. But for certain things like water, they're going to make this nice crystalline structure right as they freeze, which is going to make them get bigger. So what's specific heat? Can anybody explain what specific heat is?
The amount of heat needed to raise the temperature of 1 gram of material by 1 C or K.
Celsius or
1 degree Celsius. Okay. So look at the chart. Specific heat. So here's why this is important. It has to do with conduction. So if you've got water, for example, it's 4.18 joules per gram degrees Celsius. And lead, it says, is 0.13. Which of those? Okay, so it's gonna, you're gonna need that much heat. So the lower the number, right? The lower the material specific heat, the more its energy rises when given an amount of energy, right? So let me ask you this, which one makes a better conductor, lead or liquid water? Lead, because it's going to take, you're going to need less energy for it to warm up. Okay, how about dry air or granite? Granite, right.
Whatever's lower.
Yep, whatever number's lower is going to make a better conductor. And that's why it's important to understand specific heat, because it's really good for, and when you get into chemistry or physics, you use it a lot more. But it basically is the quality, what do you?
It's fast.
This sentence.
Oh, okay. It's basically the quality of, or the quantity, I guess, the value of a material's ability to conduct. All right. So it says here that a calorimeter, some people will say calorimeter, uses the principle that heat flows from a hotter object to a colder object until they both reach the same temperature. That was just like extra information, I think, because it really isn't related. All right, so let's talk thermodynamics.
Fine.
All right, heat and
I
thermodynamics.
love you.
So when we look at our little pot here and we consider the way that heat moves, and we look at the words at the top, our first blank is conduction, right? That's the transfer of thermal energy with no overall transfer of matter. The reason that works is because the heat energy is transferred particle to particle to particle to particle down the line,
That's a lot of particles.
right? Things have to be touching. Yeah, that's the same way electric conduction works too, right?
Yep.
All the way down the line. So a thermal conductor is going to conduct well. And what do we use if we don't want to conduct? An insulator. Okay,
Insulator.
so how does a blanket keep you warm?
It keeps all the heat in
Keep track of your body.
and then keeps
Mhm.
it cold out.
Because it's an insulator, right?
Yeah.
Fabric is
So where's the heat?
Also just feels
Coming from you.
Mm-hmm.
You radiate heat.
Where's it get trapped?
Under the blanket.
under the blanket, in between you and the blanket.
Mm-hmm. In the air.
Under a blanket.
That's what jackets.
Mm-hmm.
Wow.
So if you look at the graphic, it gives you some examples of conductors. Right, it says water, wires, it's got metal, diamonds, apparently, fascinating,
Wait, really?
and that metal chair. Okay, these are all conductors. And then it gives you some examples of insulators. Rubber. Now the same kinds of things that are good conductors energy-wise for heat also tend to be good conductors energy-wise for electricity. So this is why you don't take the toaster into the bathtub with you, because which chart is water under? Is it under the insulator or the conductor? Mhm.
So you want
Now,
us to tell you to science?
If you have a turbus, you've got a layer of plastic and space and another layer of plastic. What's in the space?
Air.
Air. So what do you suppose air is?
Air.
You want it to conduct?
Insulator.
Insulator. You want to keep the cold in or the warm in, whatever your drink is, right? If it was water, it would conduct it better and conduct it out. So this wire, right, or any other wire, I don't see the wire when I look at it. What do I see on the outside?
Rubber or plastic.
And that's called the
Covering.
insulation. Absolutely. Up on the top shelf up there on the left, there's two little silver candle holders, and there's a stick, like a wooden, an old wooden stick with a blue glass thing on it. What's that?
Wait, what?
Do you know what it is, Cole?
It caps the top. You put it on top of the power line, or they used to.
Mhm. That is an insulator, an electric insulator that they used to put on power lines, and it's glass.
Remember what year?
Year came out.
I don't know, they did them for a long time.
30s?
So it's glass, and they would wrap the wires around them, and that would stop the,
Electrician will bring the-
yes, it would stop the electric current. That's what they're for, they insulate. So they've got boots, they've got plastic, they've got foam, dirt. If you think about it, dirt makes sense. You know, people that, or animals that build their houses in the dirt way down underneath in the burrow, they stay warm in there, don't they?
They
Cave in.
Yeah. So, no, they don't cave in.
No, they stuff
It's a good
it
insulator. No, they don't cave in. They do all right. And you can wear, obviously there's mittens and things. So I asked the younger group, say we had on the table a metal box and a teddy bear, and they'd been sitting in this room at 70 degrees for 24 hours. When you touch both of them,
Will be hot.
how are they going to feel as far as temperature is
The metal
concerned?
box would be colder. Well, it would feel colder
Feel colder.
because it's
Right.
a better conductor.
The teddy bear would be a better insulator because it's going to feel
Probably feels
about the same as you. Right. All right. So convection and convection currents, radiation, and we had conduction already. So convection, somebody want to explain to me what convection is? How does it work?
Remember that lab we
The
did? That was cool.
transfer.
The which lab?
Soup and cracker.
The soup and cracker lab, yep.
That
What were you gonna say? What did you say, Ethan?
It is the transfer of thermal energy when particles of a fluid move from one place to another.
Mhm.
That's why the cracker
Dear.
soup
So-
experiment was
Y'all okay over there?
actually.
So convection tends to deal with currents, right? It says the fluid is circulating in a loop. If you've ever seen a lava lamp, y'all okay? You ever seen a lava lamp in action? That's a convection current. The little blobs of stuff get hot, they raise up to the top, they get cooler, they fall back down, and they keep doing this up and down, up and down, up and down. That's why when we did the soup and crackers lab, so last year we got a big wide pot, y'all. We got a big wide pot, and we put tomato soup in it, and we put little Ritz crackers on the top. And when we heated it up, what happened?
They moved.
They moved. And what did that model basically? Do you remember?
Convection cycle.
Tectonic plates, right? Because under Earth's surface, there are convection currents. That's what moves that's what moves our plates. That's what moves. That's actually what causes the. Is it okay?
I was just saying hi.
Oh, That's
I
actually
was
what.
messing with Aaron.
Oh, that's actually what causes the magnetic poles, because the way the convection currents are turning, the particles of lead are all going a particular direction, round and round and round. Okay, so they're all pulling one way. That causes the magnetic poles that we have. So then radiation would be like when you're outside and it's warm, or the heat's blowing and you get warm in the room because it's flowing through the medium, through space. It's waves through space. So all objects radiate energy. As an object's temperature increases, the rate at which it radiates energy increases. So the biggest source of radiation energy would be what? What's the biggest source of radiation energy?
Fire.
The sun. Right. So, okay. Look at the sun. So look at the little graphic with the pot and the campfire. All right, where's the energy coming from? Go back from there. Where'd it come from before that?
Sun.
Well, you skipped a couple phases.
Fire.
It goes straight from the.
What
sun
are they
to the
burning in the
campfire.
picture? What are we burning?
Wood.
Okay, what kind of energy is in the wood?
Chemical.
Chemical potential, right?
Nope.
Chemical potential energy is in the wood. And where did it come from?
The sun.
The sun. Through
There you
photosynthesis.
go.
And it was stored. Right, there you go. You got to the sun then. All right. So you got this chemical potential energy in the wood that came from the sun. You're burning the wood. It's producing heat in the form of radiation. If you go up like this to a fire and you're warming your hands up, that's radiation. Now, if you look at the pot, if you look at the handle of the pot, usually they put a little insulator between the pot and the handle. Sometimes they don't, or sometimes it just overcomes the insulator. But if you ever go like this, like you don't quite touch it, but you put your hand near it and you feel that it's hot, that's radiation. But the second you touch it, what is it?
Conduction.
Conduction, because then the particles are moving, energy is moving particle to particle through the handle and into your hand.
Can a fire? Can a fire conduct? Because
Can
are you
fire
ever?
conduct? That's a
Are you
good-
ever technically?
That's a good question.
Is it easy?
Ooh, I think that's a good question to research, like to look into, because that's interesting.
Is
I mean,
there a solid
Can you ever
fire?
really touch fire? Because fire's not really a solid or a liquid or
It's
Look
like
it up, Michael. See what you find.
Yeah, what's in the battery?
it's like everything. It is not solid, but anything.
A gas.
It's a
like-
gas,
in
but
between.
it's
It's a gas.
yeah. There you go. Yep. So
But the question is, can you?
yeah, there is 4. We
Right.
always like to
Touched
forget
by
plasma
water.
in science books. So then the convection there, Henry. So the convection is the soup or whatever you're heating, circling around in there, right? Getting warmer and warmer. So thermodynamics is the study of conversions between thermal energy and other forms of energy. All right, now there's such a fun thing in thermodynamics as the zeroth law of thermodynamics. I just love to say it, the zeroth.
Zero.
Here's what I don't understand. Why didn't they just make it the 4th?
Because I wanted to. Be
Why
edgy.
did they go first, second, third, and 0th? Honestly, I don't know. Somebody smarter than me probably knows.
Because it's the rule of 0. It's about like the 0th element.
Yeah, but wouldn't you make it the 4th? Because 1, 2, 3, 4. So thermodynamics is the study of conversions between thermal energy and other forms of energy. So your first law of thermodynamics, put easily, is energy is conserved. We already know that, right? Law of conservation of energy. Your second law is energy can flow from colder objects to hotter objects only if work is done in a system. So the only way you're going to get something cold to hot, because hot to cold is the natural process. If you're going to make it go the other way, you have to put work into the system, right? And
It
then, what's it
says,
say?
it says since the atmosphere is made of gases, you're touching a gas right now.
Mm-hmm.
So I guess you either always. So fire is the stuff you can see. When you get, if we're
Mhm.
agreeing on this, fire is the stuff you can see. I guess just once you're close enough to what you can see, I guess you're conducting the thing.
Eloquently
Hmm.
put.
Thanks.
That's radiation, wouldn't it be?
I don't know.
Because it's
So
waves,
there's
not
still-
particles.
I know, but it is no, because gas is made up of really fast moving particles. So,
True.
so if you're touching,
I'm gonna look into that. That's really interesting. I never even thought of that. All right, so then your third law is absolute zero cannot be reached. We've already discussed that. Now here's where your zeroth law comes in. It states that if two thermodynamic systems are each in thermal equilibrium with a third one, they are in thermal equilibrium with each other. So that basically says if A equals C and B equals C, then A equals B,
Whoa.
right? Super duper fancy. So I found this in several different graphics for you. The first one with the little circles, and that was okay, but it said transitive, and that's a math thing, and maybe not everybody's going to get that. But I liked this little hand-drawn one because I thought it made sense. As goofy as it looks, it was kind of easy to understand. So the first law, energy cannot be created or destroyed. It can only change forms. We know that. And the little bird says, like my seed, like my indestructible seeds. So there's what, 6 seeds, or 6 seeds, or no, 7, no, 6 seeds, or 6 seeds, or 6 seeds. There's 6 seeds no matter what. There's always 6 seeds. Second, entropy. Now that second law is often called the law of entropy. Entropy, which is randomness and disorder in a system, can stay the same or increase, but not decrease. Like my nest, says the little bird.
What about it?
And the little baby's coming out of it. And you have the third law. When temperature reaches absolute zero, entropy near zero. Temperature is a measure of how much molecules move, or atoms, says the ant. And then the bird says, if nothing moves, there is no disorder. And so the ants don't move. And then the zeroth one said, if two systems are in equilibrium with a third system, they're in equilibrium with each other. So there's the birds. Me and number 1 are both level with bird 3, so we're level with each other. Zeroth law, because it was added after the first, second, and third. Again, because it was added after the first, second, and third, I still don't understand why it's not the fourth.
Because it's
It's fun to say zeroth. I mean, I didn't know zeroth
that
was a
ain't
thing
a
until I
word.
heard about this. I'm like, zeroth is a thing. Henry, not appropriate. Excuse me.
No?
All right, so then we have heat engines and waste engines. So heat engines, any object that converts heat into work. Poor Aaron. Aaron, you need more sugar with lunch, more Coke.
Yes.
And then you have waste heat, which is heat not converted into work. So let's talk about heat engines. All right, you got 2 main types of heat engines. What are they?
External combustion engine and internal combustion engine.
External and internal.
I still don't put the engine.
All right, so here's how you think about external.
Yeah.
Your external combustion engine is an engine that burns fuel outside the engine, like a steam engine,
Oh.
okay? If you think about how a steam engine works, the pressure from the steam that's created is sent into the engine, but the material is burned outside, right? The fuel is burned outside. So if you think about the way an old steam engine train runs, or any steampunk item in the world that you could imagine being run by steam, you got external combustion, right? And then you got internal combustion, and this is the one we're most familiar with, right? Cars. All right. So we got cars here. Internal combustion engine is an engine that burns fuel inside the engine. So does anybody understand a 4-stroke motor?
Yep.
Okay, you want to explain it, Cole?
Kind of.
Okay.
Well, I don't remember each.
Well, it's right there in front of you too. So what can you tell us about how 4-stroke cycles? Because this is what's in your car. Okay.
So the intake stroke is when the piston pulls down, and when it does that, it then sucks fuel down into the piston's chamber, and it's the compression stroke is the next one, and it goes up, and that pushes the fuel back up, and then the cars will have the and the spark plug, but there's a device. No.
Distributor?
Distributor, right? The distributor, which will make the spark plugs fire at the right time. When it fires, it'll create a little explosion, and then the explosion will push the piston back down. And when it does that, it opens up the top again, and the exhaust can come out. But when it pushes it down, it also spins the drive shaft from this whole thing, which makes the car.
Right. So you can see a pretty good graphic in your notes, and your book had one too. So basically, if you've ever seen the distributor cap in a car that has this type of, engine set up in a way that you can actually see it, it's a little different these days, but in the Mustang, it's very easy to see. So if you have 8 cylinders, you're going to have 8 spark plugs, and they're situated in such a way that they're wired to this device that will fire them in sequence. And it should fire them in this nice, perfectly even sequence so that the motor is doing nice, perfectly even timed strokes. Now, if it's not, that's what tune-ups are for. Cars that needed tune-ups. They don't really need them today like they used to need them then. Like my car definitely needs a tune-up. So that if your car isn't tuned up well, if you have an older car, it'll do what's called missing, which means that you'll be driving along and you'll get like you'll be driving along, and you'll get this, this kind of jerky thing where it either misfired or it didn't fire in the correct sequence, and it causes this kind of a jerk in your steady acceleration.
Doesn't it speed it up with the acceleration?
Yeah, it'll speed up the firing. Yep. Now we had an issue with the car that it took me a little while to figure out because it was dark and I was freaking out because I was alone in a cemetery.
Pulled in.
Yeah, and I was like, I know how to fix it. So the whole distributor cap has another plug that goes into it to like a power cell, and it had fallen off. And I was driving the car and it just cut off, like the engine just cut off. So I coasted into a cemetery because I was going over to the cemetery to take pictures anyway, because it's quiet and there's a road with a pond. And I thought I could get good pictures of my car here, so I'm just gonna go there. Well, it died as I pulled in, and I thought, okay, it's overheated again because it was having issues with overheating. So I tried to let it cool down. Well, like 2 hours went by and I still couldn't start it. And I'd been looking under the hood and I couldn't figure out what was wrong, because when it fell off, it fell in such a way that it wasn't obvious that it wasn't attached. So it took me a while, and I thought, I'll check one more thing before the tow truck comes. And I popped the hood and looked at it with the flashlight, because by then it was dark, and I was like, oh! And then it kicked right on.
And we saw the lights in the tow truck.
Yep, and it kicked right on. So now it's zip tied, so it will come on. I don't know what else to do with it, so it's zip tied for now. I need really one of the little clamps, but I don't have one on it. So that's how a 4-stroke engine works. Now, if you look over here on the right, it's going to show you internal and external combustion engine. So this is a different angle. It's pretty similar. It looks like the one on the left, they've kind of turned the cylinder a little catty-cornered from you, whereas the one on the right, it's like you're looking at a direct cross-section. Do you see? Yeah. And then you've got your steam engine. Okay, well, look at the steam engine. Look how it's different. So you basically have this tank full of coal that they're heating, right? And it gets hot. It heats the water in the tank, and that steam expands and it goes down, and there's a piston again within a chamber. And if you look at how that works, like it'll push back and forth, and that turns that big crank that moves the wheels of the train. Does everybody see that? Mm-hmm. So that's how those function. That's how they're different, right? So those are important to know because they may just be on your exam. All right, central heating. Whoa. So heats many rooms from a single central location. Most of our houses today have central heat and central air, right? But they didn't all used to. And you used to have to go to, the parlor where the fireplace was to get warm. The cool thing about fireplaces, if they're done correctly, back when it was the only source of heat in your house, there was no central heating, the radiant heat from the fire is one thing that heats the room. But then you get the conduction into the walls. It will conduct, even if the walls are not great conductors, it'll conduct. And the heat kind of moves through the walls of the house, and that's cool. So most heating systems use convection, right? And then you got hot water heating systems, steam heating, electric baseboard. Anybody ever been anywhere where there's baseboard heating?
No.
That's wild. So baseboard heating is like
Is that where like
It
the
runs-
floors heat?
kind of, yeah, it runs along the wall, and they also have heated floors that go under tiles too. You can heat the tiles. Anybody ever had radiator heating or been anywhere with this? You've had radiator heating? Where have you had radiator heating?
My aunt used to live in a really old house in New York.
How's that work?
There was a huge radiator in my room that terrified me while I slept.
Because they make noise, don't they? Yeah. So when I was in college, the dorm room I had my junior year was on the radiator heat. The campus had radiator heat in most of the old buildings, and then electric heat in the newer ones. So the way the radiator heat works is there's a boiler, and it's central to the campus. It's a big, big boiler, right? And it sends the steam and hot water through the pipes all over the campus. They go everywhere like plumbing pipes would. And then the radiator is in your room, and the hot water and steam flow through it like this, all the little coils, and it radiates then, just like you would figure from the name, it radiates the hot heat out. But they get little bubbles and things in them, and no joke, guys, they bang. They don't tap. I mean, bang, 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 and you can go up and like sometimes if you smack them, they stop. I kept a rubber mallet in my dorm room because it would go bang, 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 and I'd go over and bang, 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 smack on it, and it would stop because they'll wake you up in the middle of the night. They're loud,
Oh yeah.
Super
it was
loud.
terrifying.
super loud. You can dry clothes and stuff on them.
Yeah.
So then cooling systems. All right, heat pumps. So a heat pump is a cooling system. It reverses the normal flow of thermal energy. So a heat pump is a device that reverses the normal flow, and you can see heat pumps in things like a refrigerator. Okay, refrigerant, that's a fluid that vaporizes and condenses inside of the tubing of a heat pump. So if you look at the graphic on how air conditioning works, do you see that? So heat pumps must do work on a refrigerant in order to reverse the normal flow of thermal energy. Radiators are a type of heat pump. Refrigerators are a type of heat pump. And air conditioners remove heat from the air. So what is the coolant in an air conditioner? Does anybody know? What's the refrigerant, the coolant that we use?
Antifreeze, is that it?
That's like in a car, yep.
Do
Do we know what goes in a, like your air conditioner outside?
Air?
Is it water? I don't
What's
know.
the one that was in the is that antifreeze stuff?
Freon.
Freon.
So Freon is condensed like they put it in a liquid form. It's a gas naturally. They condense it down, okay, and they pump it in just like propane in your tank at the grill. And that's what Freon does. So if you look at the air conditioner and show how it works, it's pretty neat. I'm not gonna make that a big part of anything you're responsible for, but it's cool. And if you stand outside by the fan and your radiator unit outside, how does the air coming, how does the air coming out of it feel?
Oh, it's warm.
It's really warm.
Is that
'Cause it's-
AC in it?
It's pulled the heat out of your
It's
house.
taking the heat out of the house.
Right. All right. So now what we're going to do is we're going to take a few minutes. I want to go over your midterm with you. All right. So your midterm, you have a PowerPoint in Dropbox, and I'm
I
trying
looked
to
at it.
convert it to a video for you if I can. I'm
I
having
tried to
issues
convert
with
it to like a with push shipping for a few hours, but it didn't work.
Yeah, they take a lot of work. So considering I had 2 of them going and whatever, I was like, Let me see here. I'm going to pull it up for you. All the junior stuff. Who in the world is so popular? Why am I popular? It was
Can I show you the
Danny.
names I gave my temperatures?
And now apparently, what now?
Can I tell you the names I gave my temperatures?
You gave your temperatures names?
Yes.
What do you mean?
Celsius is Chad, Kelvin 7,
Okay,
Fahrenheit Frank.
that works for you.
Ranch course ranch dressing. In that,
Ranch dressing.
yes,
That's
in
excellent.
That, like Ray Moore is red.
Remy, the Ratatouille.
Mermaid.
Mm-hmm.
You never watched that? Shut up.
No, I know. I didn't remember. Arcadian Mermaid.
All right,
Oh, really?
here's what I'm gonna do. I'm gonna eject it. I'm gonna scooch myself back. And hopefully you all can see it.
Yeah, can you see?
I can't see.
Hold on here.
You better.
All right. Ta-da.
Whoa!
Watch this. There.
Jazz fingers. He's printed it.
Aaron, you printed it? Yes.
All right, so here's your first.
Why are we clapping?
I know they're impressed.
It's not that important.
So, you have to know both of these definitions. Science versus scientific method. Okay?
Organized.
Process in a body of knowledge versus an organized plan for gathering, obtaining, organizing information. Okay? Most of Earth's fresh water can be found in glaciers. The curving effect of Earth's rotation has on all free-flowing objects is what? Coriolis effect. And an astronomical unit, right, is equal to the average distance from the Earth to the sun.
Australia, Mike.
Right.
Yeah, basically the same distance.
Velocity, speed and what?
The speed and the direction.
Direction. Now remember, displacement is the direction from the starting point and the length of the straight line from the starting point to the ending point. And then speed, ratio of distance to an object. The object moves in a given amount of time, right? So it's distance and time. Speed, that's what's going to be in your formula. Acceleration, what's that?
The rate at which velocity changes.
Right.
Whichever one objects.
And measured in
friction
newtons.
is the force that opposes the movement, and for gravity is the force that acts.
Right. So remember, gravity acts between any two objects.
Any
And remember that force is a push or a pull, and it's measured in newtons. Maybe those things will be put in the same sentence. You know, maybe. All right. So in magnetic force, opposite poles. Yeah. Opposite poles attract and like poles repel. You got pressure, force, distribution over an pressure is force distributed over an area measured in pascals. What do these things all have to do together? Big Bang Theory, Sheldon, and what are these other two things?
Hubble's law.
Background thing.
Hubbles law and
And then,
Cosmic
I
background.
know that.
no, not that one.
I thought it was
It's Hubble's law, Hubble's law, and redshift.
Yeah.
There won't be pictures like that, but you'll have to know Hubble's law and redshift, right? And then, of course, this guy, right? This guy is obviously related. It's in Dropbox. I'll make sure everybody has the links today when I send the email. Okay, Pascal's principle. Is it work in hydraulic systems? Sorry. And Bernoulli's principle explains concept of lift, right? And then you got Einstein saying that these things are proportional. Henry caught it. I didn't change it on your test. I think I changed it on theirs and on this one. And that they convert it into each other. That you got what? Mass and energy. And then Archimedes claimed that the buoyant force of an object is equal to the weight of the fluid displaced by the object. Put your bones away. Thank you. Okay, now this one. Doesn't want to go yet. There we go. All right, so any part of a force that does not act in the direction of motion does no work, right? Buoyancy acts against gravity. Energy is the ability to do work, and work. The rate is measured in power. The SI unit is joule. The lower a material's specific heat, we just talked about this, right? The more its temperature rises when a given amount of energy is absorbed by a given mass. Okay?
Why would you say it like that?
Yeah, it's fun, isn't it?
Why would you?
Yeah, that's the idea, is that you need to remember that, though. That it's, you could say 1 gram, you know, it raises 1 gram of the material by 1 degree Celsius, but what does it actually, like, what's the application? This is the application.
What are big and Newton?
I love them. Remember that there is really a family of inclined planes. What two other quote unquote simple machines, screw and wedge, are really just modified inclined planes? Inclined planes, okay? So also know your types of pulleys.
Yes.
Fixed, movable, compound,
And blocking time.
right? Really it just, yeah, And then wheels and axles, guys know how to recognize wheels and axles. And then you've got your 3 different classes of lever. Be sure you can recognize your 3 different classes of lever as first, second, and third. Okay. Now your test, like I said, is going to be all multiple choice except for 1 bonus question and a final question that you have to write short answer to. Okay. So what you're going to see for these are the kind of thing where you're going to have to label a diagram So it'll be like, there'll be blanks here, and it'll say, you know, A, B, C, whatever, and then you'll have the words, and you have to put them like kind of like we did on the test before, okay? All right, now here's, this is here we get fun here. So we have our laws of thermodynamics, all right? Know them and know them and know which one's first, second, third, and zeroth, right? Know your Newton's laws. For Newton's laws, know which is the first, second, third. What's Newton's first law?
First law, no, I don't know. Acted upon, is it the one about acted upon force?
It's the easy way is objects in motion.
Yeah, we'll say it.
Objects at rest will stay at rest unless acted upon. Right. So what's the third one then?
The third one is.
No, that's the Hamilton one.
Oh.
What's the Hamilton one?
No idea.
Every action has its equal opposite reaction, right? There you go. All right. So the second one is the other one. Okay. If you can remember first and third, you can bookend it. Then you know the second one's the other one, and that's the force acting on an object is equal to the mass of the object. Yes. So it's F equals ma. Right. All right. Let's see. Know your law of conservation of energy. Know what it means. Know your conservation of momentum. Okay.
Not saying easy.
Know your Bernoulli's principle. What's Bernoulli's principle, Michael?
Bernoulli's principle.
Mm-hmm.
So the less.
The easy.
Yes. Well, that is that one.
What is it?
The faster it's moving, the less pressure it has. So
Right.
The wing is moving fast because there's nothing stopping it on the top, so there's less pressure.
Right.
On the bottom, it's moving slower because the
Right.
angles making it
So there's more
so
pressure
it pushes
beneath
you
and
up.
you get lift. Right. So somebody explain the law of conservation of energy. That's an easy one. Who wants to do that? Henry.
What?
Law of conservation of energy.
Energy cannot be created nor destroyed.
It can only.
Change form.
Very good.
The amount stays the same.
Right. Okay. How about momentum?
Questions still?
Hang on a second. How about momentum? Who can do? This one's a little trickier. Who can do law of conservation of momentum? Michael, go for it. Okay.
No. So it's momentum cannot be removed
hmm
from a closed system unless acted upon by something.
Right. Okay.
Like friction.
Yep. So when a system of interacting objects is influenced by outside forces like friction, the total momentum of a system cannot change unless it's, when it's, yeah, you know what I mean. So it gives the example here of standing on a skateboard and throwing a rock. I don't know why it says a rock. Shouldn't it say a ball? I don't know who's going to throw a rock. You're not supposed to throw rocks. But if you stand on the skateboard and throw an object, what's going to happen to you? Well, if you throw a rock away from you, and you're standing on a skateboard, you're standing on it. Nope, standing on a skateboard.
Oh, it's not going like.
No, you throw the rock,
You might go backwards.
you're going to go backwards. Yep, you throw the rock, you go backwards. Henry, you had a question?
You go up
Here
one.
on the lesson 18, it says
What lesson
families
is
of
that?
11:20 and 11:22, but it cuts off there.
Till it's over.
Oh, till it's over.
Yeah, shouldn't be too long. All right, you may have to label this. Know it, okay?
Oh, yeah.
You may have to know that, potentially label it.
Why does it just
You
say
know
what's
it.
that first one?
It's just showing you a hydraulic system, right? And then, oh, this one looks really familiar, maybe because we saw it today. Uh-huh. He's awake.
How's it
Okay, when we did the triangles, we did the Felicia will die and the DMV. We didn't really focus as much on this one. You should go home. Here's your big tip. You should go home and memorize this one too, because you may have to label these.
What's the T?
So that's time. So it's time, distance, and speed. What'd you say?
Yeah, it's just
What is it?
forward DMV. I'm not sure.
Oh, forward DMV, and you're not sure? You're sure. I'm just not going to repeat it. I'm sure it's something filthy. All right. So does anybody have one? Anybody have one we want to use for that?
To die someday.
Maybe.
Everyone's got it out.
I think the other kid said something like Tony died Sunday or something like that. I don't remember what they
Tony
said.
Stark, he died.
It's true.
Stop.
There we go.
What's so cool about that?
Ready to face the emotion.
Come up for one.
Like father, like son.
You're gonna want to know this. You're absolutely gonna have to label this. And then, oh, and so your test it's 50 questions. So it's 2 points apiece.
Wait, 50?
Yeah, I think so. I'll double check it.
You said
I think it's 50. Yeah. All right. You may have to label this. All right. And you may have to label that. So this is your independent / what's our book column?
Control.
No, what's your book called independent? Manipulated, right. And what is your book called a dependent variable?
Like changing.
Responding, right. And then control is control, right? So your independent is what you change, your dependent is what you observe, and your control is what you keep the same. All right, now you may have to write a short answer to this question. You're really going to want to understand it thoroughly and completely. We covered it, didn't we? Back in like lesson 1 and lesson 2, we went over and over this. Define both scientific theory and scientific law. Explain how they are different and use an example
If I do it
to
now, do I
illustrate.
have to do it later?
Yeah, to illustrate your explanation, right? So you have to come up with an example. You have to know before you get here that not only do you have to explain this, but you have to have an example. So get an example, Henry. So get an example in your head, right? You're gonna want to have that so you know what it is. All right? I'm gonna save these as JPEGs so you can whip through them like flashcards, but they won't be blanked out, right? So, and I'm gonna, yeah,
JPEGs.
yeah, JPEGs.
It's another way, it's another
Pictures.
file
It's like
format.
PDF.
I look like I know.
Obviously, not. It's like a
You should.
It's already
I
as
know how much coding you do. You really should.
it's already as a PowerPoint, and I'm gonna try and see if I can get it into a video. But for you guys, it may be easier to just do it as JPEGs. So that's where it is. The PowerPoint has timings, so if you just sit there and watch, the answers will pop up.
I like
Mhm. Well, you can always move faster. Does anybody have questions about the exam? So what time are you supposed to be here for class?
11:30.
You tell me. Somebody look and tell me.
9:45.
No, it's 9:30, not 30. I thought you were
10:30.
I
It's
live here.
on your syllabus. Look it up. When are you supposed to be here?
10:30.
10:30 to 11:15.
Okay, so
Quiz happens. Then
Yeah.
someone there starts from 11:30 to
so you
1
have
p.m.
45 minutes. All right, now that's something to consider. How many questions did I say you had?
50.
50 questions. And how many minutes do you have for this quiz?
Right back.
Okay, so what does that mean?
So you have a little less than a minute.
Little less than a minute, which means that these multiple choice ones,
You have to
Needs to go
you
live.
gotta fly, right? Yeah, you absolutely have to fly through them. I'm gonna real quick.
Can we like phone a
I'm
is
sharing
there, like,
my
any phone a
inner
friend
phone.
option if we don't
Nope.
share
Channeling my
one?
inner
No phone a
public
friend.
schoolers
Next
until
week,
I-
right?
This is next week,
Or ask
Next
Google.
Honestly,
next Tuesday.
I'm sure it's like math study.
You're totally capable. Every one of you is totally capable.
There's no phone a friend or ask
There's
Google.
no phone a friend. There's no ask Google.
This isn't. who
Yeah.
brought me in.
Katie's gonna
Ask the
come and
audience.
help me proctor.
What if I ask Katie?
No, she doesn't know either.
No,
Yeah, she
that's
does.
So just so you have an idea, real fast, this is, you can't see the questions from here, but this is what they look like. No. But it's gonna look like this, right? This is what you're dealing with. See?
It's my
So you see that you're gonna have to answer fast, right? And if you're somebody who writes slow and you need additional time for writing, that's fine. You can start early,
Please.
okay? So if you need additional time to write, you can write early. That's fine. Yeah, because the younger group arrives at, hold on. The younger group is arriving at 10. You guys arrive at 10:30. They go from 10 to 10:45. You go from 10:30 to 11:15. If you want more time, I have no problem letting you have more time. You have to come early.
They're in a different room, are they?
We're all kind of spread out on this level. I don't want anybody upstairs, but we'll have, this table, this table, this table. We'll have the dining
Some
room
people sit
table.
on that.
We'll have the, I might put a chair up here. We'll have the card table pulled out. We'll have you spread out wherever. And as long as everybody has wrapped up by 11:15, we're good. So the younger group, I'll reiterate to them that if they need to go longer, they can go longer. They have, some of them have trouble writing. So,
Do we still have Spanish that day or no?
we need to ask Miss Jackie, but I don't think so because we're gonna
We
start.
don't have Spanish.
I don't know. We need to ask
Not
Miss
today.
Jackie
Not
because
today.
we're gonna start our
We
movie.
have it today.
Now today you have Spanish, but we're gonna start our movie.
That was a
It'll
look
go
of
till,
pure joy and then pure defeat.
but the movie should go till about 1 o'clock. So there's still time for Spanish if she wishes to do, because the movie should be done around 1:15. All right.
Yo, Tango.
Oh, huh?
Probably.
Yo,
That
Tango.
was last. That was like way long.
Yo, Tango.
Way long ago.
Oh, that's
All right. So everybody, does everybody understand what's expected?
Yes.
Okay. Here's what I highly suggest you do.
Study.
Highly suggest. You've got 12 minutes till your class with Miss Jackie. You should do the PowerPoint together, or you could, I'll try and get it up there. I don't know that I'll succeed. Aaron's got the cards over here printed out, okay? You should practice that together, get it done, and do it as much as you can, because like I said, you don't have time to really think. You gotta know. So that's what I wanna know is, do you know, right? And some of them
Nice.
are, duh, gimme, you have to know. But some of them are pretty you actually have to know, right? And I'm gonna use this thing like this to hold it up to your paper and grade it while you're here, while the movie's going. So if there's anything you owe me, hang on.
Oh.
If there's
Can I
any,
take a picture of that?
if there's
No.
anything you owe me that you haven't given me, I can't give you a semester grade next week. So if you have everything done, preferably get it to me before class.
But I don't
Like
know.
email it. No, you'll know because all you have to do is log into your gradebook. It's all there. If you have something that you owe me and you want to actually get a grade when you leave class next week, don't come to class with it. Send it to me before because it gives me time to grade it and return it. Right? All right. So, okay. I'm going to go see if I can figure out why the TV wasn't doing its thing. But why don't you guys sit here as a group and somebody pull up the Dropbox. You can pull it up on your phone or whatever you need to do and see if you can figure it out, okay? All right, and I'm gonna stop sharing for Kai and Ivy. Later, guys.
Yeah. Say Rana.
Say what?
Yeah.